Hello and welcome to the video on reaction mechanisms. So, in this sort of lesson, we're going to learn sort of how exactly a reaction happens. So, what molecules are actually colliding into each other, and what order are they colliding into each other? And it's actually this reaction mechanisms that actually helps determine the rate laws that we've been determining. So we've been sort of determining it using data, but those rate laws are supported by a reaction mechanism, how the reaction occurs. And we're going to take a look at reaction mechanisms right in this lesson. So, most chemical reactions that occur in multiple steps, not just one. And if you remember when we were doing like delta G and delta H, we did something called Hess's law. We added up the individual steps. And remember that was called Hess's law. Now, each individual step of a reaction mechanism, okay, is called an elementary step. Okay, and each step describes a molecular interaction between molecules, usually collisions. Okay, and elementary steps cannot be broken up further. They're the simplest they can be. Now, I remember I think I said this rather loudly. The stoichiometry of an overall reaction cannot tell you the rate order. So when there's a 2 in front of a reactant in a reaction, that doesn't tell you, okay, that the reaction is second order, okay? But if you're looking at an elementary step, okay, that does tell you the order for that step. For overall reactions, the stoichiometry doesn't work, but it doesn't work in terms of the rate law, telling you the rate law. But for elementary steps, it does. It does tell you, the stoichiometry does tell you the rate law. So in an elementary step, if there's a 2 in front of a reactant, that means for that reactant, the reaction is second order. Okay? That's only true if something is an elementary step. And that will make more sense as we look at some mechanisms. For a lot of this PowerPoint, we're going to be looking at this reaction. So this is the overall reaction. Okay? And then this is the proposed mechanism for action. And if you take a look at what the mechanism is proposing, what it says is first, a molecule of H2 collides with a molecule of ICl. Okay? And that produces HI and HCl. And if you take a look, we got one of our products, only one of them, which is HCl. Then in the second step of the reaction, HI, which was produced in the first step, then collides with a molecule of ICl. Notice that there's 2 of them in there, producing another molecule of HCl and the I2 that we need. Okay, so that's the proposed, that's what those reactions propose that is how this reaction occurs. Okay. Now notice, if you sum these up, so if you sum these reactions up, and I can't find my smartboard marker, hold on a second, I need to pause this. So, smartboard marker has been found. So if you notice, just like when we did Hess's law, if you add up these 2 reactions, so this cancels because it's on both sides, and if you add it up, we have H2 left. Whoa, that's not what we want. We have H2 left plus 2. Why does it keep on doing that? Plus 2 of these. It's going to do it again. So, all right, I give up. I'm going to write it with the damn mouse. So we have 2 ICl here. If my technology wants to cooperate, that would be wonderful. It does not. So then these add up to 2, right, which is here. You can fill this in yourself. And then we have the arrow, all right? And then what's left on the product side is 2 HCl, which we have here, as my mouse likes to disappear, and then 1 of the I2. So we see that that is what's left. And the fact that this is doing this is really making me angry. So, anyway, the point is that this mechanism adds up to the overall reaction, just like when we were doing Hess's law. Okay, now there's a new vocabulary word here. Okay, and that is the word intermediate, and HI is an intermediate. Okay, the reason why HI is intermediate is that it's a molecule that forms in one step and then is used up in the second step. Okay, and the AP exam loves to have you identify intermediates. Okay, but once you say it's not present in the reaction, it's made in the first step and then used up in the second step. Okay, and that is an intermediate. A little bit more about intermediates later in this presentation as well. Okay, now, there are 3 types of elementary steps that you can have. Okay? So the first type of elementary step is unimolecular. And that's really when there's only one reactant, and it's actually just rearranging itself. And an elementary step that has only one reactant with no stoichiometry would have a rate of rate equals K to the A concentration. And now my phone is ringing. So just to summarize what I said, since I got interrupted by a phone call. So if you have a elementary step that is unimolecular, meaning that the reactant just rearranges, the rate is equal to K times the concentration of that reactant. Now, bimolecular elementary steps are when two reactants collide. Okay? And again, as I said, okay, when it's an elementary step, the stoichiometry can or does predict the rate law. So here we have two of A colliding, and this is the rate law. You can see the square there. And here we have A and B colliding, and this is the rate law here. Now, termolecular reactions are very, very unlikely. Okay, so usually they don't describe the rate law that often. They're unlikely to occur and usually not accepted in mechanisms. Okay, if you think about it, for a bimolecular collision to occur, two molecules have to hit with enough energy and also in the right position or right orientation for this reaction to occur. Termolecular, you have to have three molecules come together with enough energy and three molecules in the right position for the reaction to be successful. And that's difficult. So termolecular elementary steps are very, very unlikely and don't occur that often. But unimolecular and bimolecular often occur. Okay. So a mechanism is just a hypothesis. It's very, very, very difficult to prove mechanisms. You can only say that a mechanism is consistent with the rate law that you get from your data. And we saw two ways to get rate laws. Either using the integrated rate law or using like the initial rates and doubling the one and keeping one the same. Okay. So it's very, very hard to prove a mechanism. It can only be consistent with the data or consistent with the rate law that you got experimentally. However, okay, for a mechanism to be valid, three criteria have to be met. Okay. First criteria is that the elementary steps have to add up to the overall reaction like we just saw. Okay. The mechanism has to be consistent with the observed rate law, which we get from doing experiments, which we've been doing the past week or so. And then the elementary steps have to be reasonable. And they should usually only be unimolecular or bimolecular. Termolecular, the one with three, rarely ever occur. And they really shouldn't be included in mechanisms. So in a mechanism, there are two types of steps. Okay? There are slow steps and there are fast steps. Okay? Now, the factors that determine whether a reaction is going to be either slow or fast, okay, are the categories for collisions or the qualities of a collision. Okay? So a step that requires a lot of energy to occur and a complicated orientation of molecules is going to occur slowly. Now these two sort of qualities of a collision make up activation energy. So if a step requires a lot of energy of collision and a complicated orientation, they're going to have a high activation energy or a high activation energy barrier. Okay, now, the step that is said to be the slowest is known as the rate-determining step. Okay, and it is the step that determines the rate law for the overall reaction. Okay, now, just to give you an idea about a rate-determining step, think about like if you're going to New York or a trip to New York or, I don't know, even like a trip to like someplace West Hartford. You know, in my trip to New York, the rate-determining step of how long it's going to take me to get to New York is when I go on the Long Island Expressway. When I get over the bridge, and there's a sign, okay, and it either says traffic moving well on the Long Island Expressway, or it says delays, okay? And if it says delays, my trip, which should take 2.5 hours, might take 4. Because the Long Island Expressway is a freaking parking lot, okay, if there's traffic on it. So the rate-determining step is the step in the reaction that determines really how fast the reaction is going to go. Okay, now, here we're looking again at this reaction. Okay, so again, this is the reaction that we looked at in the first slide. If you just looked at the stoichiometry for the overall reaction, which you can't do, okay, you would predict that the rate would be like this. If you thought that in the mechanism of the reaction, a molecule of H2 collided with 2 ICl, this would be the rate law. And again, that collision is unlikely. It's unlikely that three things are going to collide with enough energy and in the right position to have a successful collision. Okay? It turns out, if you try to determine the rate law experimentally, this is the rate law. So we know that this reaction must occur in more than one step because the rate law is not consistent with the overall reaction. So, if we take a look at the mechanism, or the supported mechanism for this reaction, we'll see these are the same steps that we looked at the beginning of the presentation. This first step is the slow step. So this is the rate determining step. Okay? And the second step occurs quickly. And as I just said, okay, if the slow reaction occurs first, if the slow reaction occurs first, it determines the rate law. Okay? So if we take, so in this mechanism, the slow reaction occurs first, or the slow step occurs first, and the rate law is consistent with the stoichiometry in the slow step. We see that the rate law is equal to H2 times the concentration of ICI, which is in the first step, times K. Okay, so when the slow step occurs first in a mechanism, the rate law, okay, is consistent with the stoichiometry of the slow step. Now, if we look at a energy diagram, which they love to link energy diagrams to mechanisms, we see that this is the energy diagram, and I apologize for the bad font. This is an energy diagram for this mechanism. And we'll notice that the first step is the slow step, and it has the high activation energy. So the hump here is higher. And then the activation energy for the second step is lower, because this step is fast and has a lower activation energy. Okay. Now, for the slow step, which has the higher hump, okay, step one, I know you might not be able to read this text, has a higher activation energy, therefore a smaller K, because it occurs slower, and it determines the overall rate. Okay. Now, you'll notice here we have a hump for the activation energy for the first step. And then there's a sort of like, a little valley here. In the valley is where the intermediate is. Okay, so remember we talked about the intermediate is the thing that gets made and then is used up. And we said that the intermediate here was HI. So here is a location of the intermediate, HI. And then HI reacts, overcomes a smaller activation energy. And that's why that hump there is smaller. Okay, now, and they rarely ever ask this, at the top of the hump of each activation energy, something called a transition state. Okay, these are very, very unstable. And they're sort of the state between these being products and these forming, these being reactants and these forming products. So this is the transition between H2 and ICI becoming HI and HCl. And that is sort of at the top of the hump. Same thing for this transition state. So at this hump of the reaction, that is sort of the transition between HI and ICl becoming HCl and I2. So it's sort of like here bonds are beginning to break and beginning to form at the transition step. And remember here, okay, we have the intermediate of the reaction, which in this case is HI. Also, just as a review from our thermodynamic unit, this reaction is exothermic because the products have less energy, so therefore energy was released. So if you notice, the reactants here are higher than the products, donating that delta H is negative, or the reaction is exothermic. Okay. So if you look at the next slide, there's sort of a summary. And so again, the point, and I'm going to summarize this briefly. Again, that if the slow step is first, and I would write this down on this slide, if the slow step is first in the mechanism, it determines the rate law. The stoichiometry of the first step determines the rate law. And that is sort of the overall summary or the overall importance of this. We did learn about intermediates and energy diagrams as well, and that stuff is important, okay? But the most important here is that if the slow step is first, okay, then it determines the rate law, okay? And its stoichiometry determines the rate law. All right, this lesson is going to continue, so I'm going to upload this and then finish the rest of the slides, which should take about another 5 minutes or so.